All right, we are going to go ahead and get started on section 2.4, linear functions and equations. There are 4 objectives for today, and a lot of this is going to be real world problems and just being able to define graphs and piecewise functions. So the first example is through linear modeling, and this again is a real world example. In 2002, the average number of people in the new apartment complex was 30.2. Just so weird. How do you have a 0.2 person? But that's the average number of people. So obviously, we're not talking about the actual number of people, but the average number of people. It increased by 20 people every 3 years until 2014. So let's write a formula for this equation that models this whole situation. So to do so, we need to start. With either the initial value or the rate of change, or we need 2 points. So what all do we have in this situation? We know that in 2002, we had the 30.2. So we kind of have a point there, 2002 and 30.2. But then we also have a rate of change. So we have our slope, and it says an increase of 20 every 3 years. So we have 20 over 3 as our slope. So we have a point and we have a slope. It doesn't look like we have 2 points though. So maybe we're going to use point slope formula. So we can actually go backwards and find our y-intercept. But we can kind of redefine x so that we're looking at that initial year. Instead of calling it 2002, we can say that that is our 0 year. Like that is our initial value. So we can say that this is our y-intercept in so many words. Okay. So then after year 1, we have our increase, and then year 2, then year 3. Year 3 is where we would see a 20-year increase, because it says it takes 3 years to increase by 20. So we can imagine that this would be 50.2. But that looks so weird compared to that. So that's a question that I have. Let's come back to that. Okay. But what we're going to do, it says that we could actually treat this as a y-intercept instead of just any random point. And then we can put this together in slope-intercept form. And x would represent the years after 2002. So x wouldn't represent 2002. X would be 0 when we mean 2002. So taking this down, state what the input variable represents in the domain of the function. So if we say that x is representing years after 2002, then we only can go from 0 to 12 because we're only stopping at 2014. So from 2002 to 2014, this is 0, this is 12. There's a 12-year difference between the two. State what the output variable represents and the range. So the output in this case was the number of people in the new apartment complex. And it started at 30.2. That was our lowest value. Okay. And so how many ever we get in 2014 would be the highest. So the output value represents the average number of people. Because the rate of change is an increasing line, we know that the minimum value is 30.2. And the maximum value is given in 2014 or whenever x is 12. So we plug in 12 and we see that that is 110 people. So our range is going to be from 30.2 people initially at the 0 year or 2002 to 110.2, 12 years later, 2014. Now we're doing a different example here. It says the graph shows the distance in miles between a runner and home after X hours. So how many miles did the runner start from home? So this is time in X-axis. And then we have distance from home in miles on our y-axis. So at the very beginning, he was not at home. It looks as though he was 1 mile from home. So therefore, he started a mile away from home. Is the person running towards or away from home? Because his distance from home is increasing, so after 1.25 hours, he's already 10 miles from home, and then 15 miles from home at 2 hours. We know that he's running away from home because the distance is increasing. How far away from home is the runner after 2 hours? It looks like he is at 2 hours. He's 15 miles from home. And that point is 2:15. Okay. Continue with the same example. It says, find and interpret the slope. So to find the slope, we just find 2 points on this graph. So 0, 1, I would say 0, 1, and 1. What is that? 8. And we can find the slope that way to say there was an increase in 7 miles over 1 hour. Okay. The textbook uses 0, 1, and 2:15, and they say there was an increase in 14 miles over 2 hours. Still the same thing. 7 miles per hour. So it doesn't matter if you choose a bigger span or the closer one, just choose 2 points that are on the line. Okay. Write the formula. So to write the formula, all we need is a point and a slope, or to know the y-intercept and the slope. And because we know our y-intercept is 1, we know our slope is 7. We already know our equation is 7x plus 1 because of mx plus b form. There we go. All right, example 3 is a different example, but now we're giving it as a table. So if you notice, example 1, we were given our problem as words. So we had all words. And then we moved to example 2, where we actually had a graph, and example 3 is through a table. So basically all these problems are just giving it to us in the different representations that we can see linear functions. Calculate the slope of a line that connects these consecutive points. So we're looking, again, slope is always going to be change in y over change in x. So looking at the change in y, that's a 310, and the change in x is 5. So I'd say the slope is 310 miles per 5 hours. You can always reduce that. 62, I believe, over 1. But let's see. Perfect. It's not the same in every interval. So that first change is just this first one. If we look at the change from here to here, then we get 62.4. And if we look at the change from here to here, then we get 62.6. And how do we know that there were different slopes? Well, it says calculate these slopes of the line segments. This is not one continuous line. These are different line segments. So find the linear model that models this data. Well, if it was a straight line, we just take the 62 and then work backwards to find 0 and go from there. But in this data, we're going to have to do it a little bit differently. To model this data, we can approximate the rate of change by averaging these together to find out the average rate of change. That's how we had the average number of people in the house was 30.2, and it's like, you can't have no 0.2 person from example 1. So we'll find the average, and the average is about 62.3. And if we were to say 0 hours, well, that would have meant 0 miles were traveled. Because how can you travel any miles when you have no time travel? Like that doesn't make sense. You know what I'm saying? So we just say that our y-intercept is 0. And because that is the case, when we substitute these values in, we just get 62.3 times x. And we can approximate and see if that really works. Like, let's say our equation is 62.3 times x, which we got 63.2 because we had 3 different slopes and we had to average them together. But and let's say we're gonna go for 20 hours driving, 62 miles per hour for 20 hours. Use my calculator. I got 1,246. Notice that that is not the same as this, but it's close. And the reason is because it's an estimate. It's not the exact values because this is not a linear function. It has little parts of linears, but it's not linear altogether. So if we were to graph this, it may look like this. So it's linear, but it's not straight linear. That is called piecewise. So we're gonna actually define these functions now. In this next example, a function f that models data and is defined on pieces of the domain is called a piecewise defined function. If each piece is linear, the function is called a piecewise linear function. An example of a piecewise linear function are the, I cannot say this word, Fujita or Fujita scales, which we classify tornadoes by their intensity. So like how intense this tornado is goes on this scale. Whether it's a category 1, we probably know more about hurricane scales, but category 1 tornado, a 2 tornado, a 3, a 4, a 5, based on the wind speeds. So let's say on the F scale for a tornado, having wind speeds of 40 to 60 miles per hour, that's basically where it starts. It's telling you it has to have 40 miles per hour speeds before it's even considered a tornado. And then 260 is the cap for category 5 tornado. So let's say estimate the minimum wind speed for F4 tornado. So if it's going to be a F4 tornado, it's going to be in between. This looks like a little bit on the other side of 150 to on the other side of 200. Okay. So about 160 miles per hour is the minimum for F4 tornado. Evaluate and interpret F of 100. So if the wind speed is 100, that's here. So that means that we're in an F2 tornado. A continuous graph can be sketched without picking up your pencil. There are no breaks. So is this continuous? No, because you're going here and then you have to pick up your pencil and go here. Pick up your pencil and go here. Pick up your pencil and go to the next and the next. It jumps. And so that's why it's called a piecewise function. One thing that I think you should ask yourself is, why do these circles have holes in them, whereas these are filled in? And the reason is because from 40 to, I'm gonna say 80, that's considered a F1. But as soon as you get to 81, not 80, because 80 is still a F1, but 81 miles per hour, then you move to a F2. And that goes all the way to 110. But then 110 is still a F2, so it has to be 112. So that's why an open circle at 110. Those open circles mean that is considered at the bottom, at the level below. So this is not continuous. Another type of piecewise function is where maybe it is continuous, but it's not like straight linear. It does something with one slope and then it changes slope and then it changes slope again. So an individual is driving a car along a straight road. The graph shows the driver's distance from home after X hours. So the distance from home, you're already 30 miles away from home when you start. Then it looks like they're traveling. After 2 hours, they reached their destination, which was 110 miles away from home. They stay there for about an hour. They get back in their car and drive back towards home, where they then make another stop after an hour. So you can kind of see what's happening. They are stopped in this case. They didn't change distance, going back home. And this way we're going away from home. Okay. Use the graph to evaluate f of 1 and interpret what it means in the context of this problem. So f of 1 is here. And so that is what, 60, 70 miles per from home. So I would say after 1 hour, this person is 70 miles away from home. Is F continuous? Yes, you didn't have to pick up your pencil when you drew this whole thing. Uh-oh. Identify where F is increasing, decreasing, or constant. Write your answer in interval notation. So it's increasing this first stamp. Let me choose a different color. I'll highlight. We're increasing here from 0 to 2. So for 2 hours, we were increasing. We began, the car is constant from 1 to 2. I'm sorry, from 2 to 3, because they didn't go anywhere. It was just stopped. And then the car is decreasing between 3 and 4. Actually, I don't know if it's decreasing. Yeah, it looks like it. Let's see. There we go. An individual is driving a car along a straight road. The graph shows the driver's distance from home after X hours. So again, we have the same situation. Describe the motion of the car for each line segment. Include the starting point and the meaning of the slope for each line. So starting at this first piece, from 0 to 2, the slope is 80 because we went 80 miles in 2 hours. So the slope is actually 40 miles per hour. That's horrible. Whereas right here, the slope is 0. And right here, the slope is negative 50. Because you went down 50 miles in 1 hour. It's not that the speed is negative 50, it's that he's driving backwards, not backwards, driving back towards home. So the car starts 30 miles from home. The car drives away from home at 40 miles per hour for 2 hours. Then the car doesn't move for an hour. Last, the car drives towards home at 50 miles per hour for 1 hour. We could also describe each part using equations. So 40 miles per hour, starting at 30 miles away. Then he stays at 110 from 2 to 3. And then from 3 to 4, drives towards the house. That's the negative 50. At 50 miles per hour. And we have to say plus 260. And that's because if we were to extend this line, it would have crossed up here 260, which would have been our y-intercept. Says interpret f of 1.5. So 1.5 is when he's still driving around here. So you just put 1.5 into the equation right here. 40 times 1.5 plus 30. And that's 90. So he was about 90 miles from home after an hour and a half of driving. All right, using the piecewise function again, use g of x to complete the following. So we have two different scenarios for the different parts of our graph. So it says, what is the domain of g? Well, g goes from -3 to 3. But it doesn't, it has like a break at 0, but 0 is still continuous because 0 is included here. Now, had this been 0 is less than x, less than or equal to 3, 0 would not have been included in our set. So we would have to write this in two different intervals. But because it's continuous, it didn't include 0 here, but it picked it up here, we can say the 0 is in our set. Evaluate g of -2, g of 0, and g of 2. So g of -2, well, -2 is between this interval. So we put -2 in this first equation. And we say 3. In the next one, we say g of 0. 0 is not included in this first one, so we have to go to the second side. And so we say g of 0, we're going to use 1/2 x for that one. So it's really 1/2 times 0, which equals 0. And then the last one, g of 2. 2 is in this second set as well. So g of 2, 1/2 times 2. 1/2 times 2 is 1. So g of 2 equals 1. Okay. And let's keep going. We're going to sketch this piecewise function now. So we know that two different things are happening on the different intervals, but let's see what it actually looks like. To sketch the graph, we have to find points at the endpoints of each of those segments. So we'll plug in -3 and we get -3, 4. If you plug in -3 to this x, and then you're going to plug in 0 to get the other endpoint, and you get 1. But it's an open circle because it's not included. So then we connect those two dots. Okay. And then we do the second part of this, which is 1/2 x. Plug in 0 and we get 0. So 0, 0. Then we plug in 3 and we get 1/2, 1.5. So at 3, it's 1.5. That will be a point on our graph. And we connect those dots. And then it says, is it continuous? The answer is no, because I'd have to pick up my pencil to draw the whole thing. So it's not continuous. There's a break in the domain. All right. So that's piecewise functions. The last concept, I think this might be the last or second to last, direct variation. This is just basically a linear function, but we don't have a y-intercept. It goes straight through the origin. At 0 is 0. Okay, the y-intercept is always 0 in a direct variation equation. Instead of saying mx, we say y equals kx. And we're talking about constant of variation, but it's the exact same thing as m. It's slope. It has a new name, constant of proportionality or constant of variation, but y'all, it's the same thing, okay? So it says y varies directly with x. That means y times kx. And suppose that y equals 23 and x is 7. We don't know what k is. So we solve for k, divide by 7. Oh, I'm sorry. I'm gonna use the text that's already on the board. Okay, so you plug in 23 for y, 7 for x, and we solve for x, solve for k. So k in this case is 23 over 7. So now we can use k to find out what our y is whenever x is set 11. So again, we have y equals kx, but this time we're going to substitute 23 over 7 in for k and 11 in for x. And we multiply that together, we get 253 over 7, and that is our y value. Of course, you can write all of this in decimals if you want to, but my math lab will most likely ask you to leave it in decimal format, fraction format. The table shows a number of seconds of music that can be stored on X gigabytes of storage space. This makes sense because if you have no space, that means you have no storage. You have no songs. That's why your y-intercept is 0. That means that you're going to start off at 0, 0, which means that we're in a y equals kx type format. Okay. So this is saying if you have 0.13 megabytes, then you can listen to 6.11 seconds. This is telling you how many seconds you can listen to with all the sound that you have. So you can choose any of these to figure out the constant of proportionality. So let's use the first one, 0.13 for x, 6.11 for y. Let's solve for k. K is 47. So that's our slope or our rate of change. Now we use that to find this value. We have our y is 54.52. We have our k, 47. Now we need to solve for x. Okay. So divide by 47 and solve for x. X is 1.16 megabytes. So 54.52 seconds of music can be stored on a 1.16 megabytes of storage space. True story, we used to listen to music like this and think about this when we bought iPods. If k is not the same for all the points in the table, but are very close, then you can just approximate k by averaging. So if you go back to that very, I think second problem we were doing with the 62, the 62.4, the 62.6, we can take an average of the k values and then use that to find our value. The last problem is Hooke's law, and it's just a direct proportionality problem. And so we have a 15-pound weight that is hung on a spring and it stretches 5 inches. So find the spring constant. So F equals kx. Okay. So we'll have 15 is our force. That's the 15-pound weight. And then it stretches, that's x, the 5 inches. So let's solve for k. In this case, k is 3. Okay. So then we need to find out about a 32-pound weight. So we'll have 32 for F, 3 for K, solve for X, divide by 3 on both sides, and X is equal to 10.7, about 10.7 inches that that spring constant would pull it down by, would stretch that by. And that is it for 2.4. We'll talk about it in class on tomorrow.